You can also listen on iTunes, Google Play, and SoundCloud. This is Mission Control Houston.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Would you like to be able to see into the future? That is an intriguing question that has been contemplated time and time again throughout human history. Famous stories from the Oracle of Delphi all the way to the hysteria around the Mayan calendar in modern times have in some way dealt with the idea of humans seeing into the future. This idea has shaped popular culture and our science fiction with that one tantalizing idea of what if. In the real world, the answer to the question of can we see into the future has been answered with a resounding no. In our ever-evolving society, the trend today is to look toward the future by relying on predictive modeling to best predict the probability of an outcome. But we all know that even these well-thought-out predictions based on data often turn out to be not so predictable. Although it's clear that future events remain virtually unknowable, there is one group within NASA that comes as close as you can to seeing into the future. Throughout NASA's field centers, members of the Fixed Wing Project team are peering into the future every day and coming up with concepts that they believe will be on the next generation of aircraft. Because it takes years to plan and develop these concepts, the hardware and theories that are being tested today will be key components that enable the next generation of aircraft to take flight. On this episode of NASA X, follow us around the country as we visit members of the Fundamental Aeronautics Program's Fixed Wing Project, who are developing the framework that will shape how aircraft of the future will fly. Take a look behind the gates of NASA to see what some of these new ideas look like and how the engineers of NASA are paving the way for the ideas that will change the future of flight. To the untrained eye, most of the aircraft of today look very similar. This is because over the past century of flight, aeronautical engineers have worked hard to optimize passenger aircraft to the point where they are as efficient and safe as possible. As a result, the basic tube and wing shape has been configured and examined from every possible angle, making it the most efficient design possible today. Although aircraft have looked basically the same over the past few decades, if you look closely, you can see some of the major design changes. Wings that were once swept back more dramatically now are less so because of advances in aerodynamic shaping. Engines that spewed emissions by the ton are now much more efficient. Materials that were once so heavy that they significantly weighed down a craft are now much lighter and stronger. With all this improvement and efficiency, it is fair to ask if there is anything else that can be done to make flight even better. The answer is of course yes. Behind the gates of NASA, there are scores of researchers who know that we can still make aircraft better because they are working toward these long-term goals every day. Some of these researchers from the Fixed Wing Project are working on so-called N+3 configurations and goals. In mathematical terms, the letter N is where you start now. N+1 is the next step. N+2 is just beyond that, and so on. Here in the Fixed Wing Project, N+3 equates to aircraft that will be flying in around the 2030-2035 timeframe. For this team, everything is on the table, including engines, fuels, wings, and fuselage shapes.
Well, we need to remember the first A in NASA is aeronautics. So it's a National Aeronautics and Space Administration. Aeronautics is the field of research for airplanes. The airplanes that will fly today were researched and experimented within NASA many years ago. So we're trying to continue that tradition, that important work that we have done for the nation and the world for 20, 30 years from now. Fixed Wing is a NASA research program in where we are doing activities to try to improve the airplanes that we're going to be flying in the future. We're trying to make them less noisy. We're trying to make them better for the environment. We're trying to make them in a fashion that they will use less fuel.
The research we're doing is important because air travel it's such an important part of your life. People travel, even if you don't travel. Cargo gets carried every single day. You use something every single day that gets carried by an aircraft. It's part of our way of life these days, and it often gets taken for granted. There are challenges though, so we are focused on exploring and developing technologies and concepts to improve the energy efficiency and environmental compatibility of transport aircraft.
With this mandate to significantly lower noise and emissions and increase performance for subsonic aircraft, there will be a need to address virtually every aspect of the current aircraft configuration, including developing new materials and engines, testing alternative fuels, and even changing the fundamental shape of the aircraft. All across the country, fixed-wing researchers are doing just that. Major advancements are being made into the understanding of how future aircraft will fly. Because there are so many areas of study, let's first look at something that has the potential to be used today as well as in the 2030 timeframe: alternative fuels. On this beautiful morning at NASA Dryden in California's high desert, a test called ACCESS, or the Alternative Fuel Effects on Contrails and Cruise Emissions test, was performed to study the effects of alternate biofuel on engine performance, emissions, and aircraft-generated contrails at altitude. For this test, 2 aircraft were flown in tandem. The first is NASA's DC-8, which will be burning an alternative fuel. The second aircraft is NASA's Falcon that will fly directly behind the DC-8 to measure and characterize the emissions coming out of the engines from the alternative fuel. Here is NASA's Bruce Anderson to explain.
NASA's role is in assessing the combustion characteristics of alternative fuels, as well as determining how these fuels will affect the performance and emissions from aircraft. To understand how aircraft affect the climate, we need to make measurements at cruise altitudes. So the focus of ACCESS, or the alternative fuel effects on contrails and cruise emissions, was to fly behind the DC-8 in flight and look at its emission and contrail characteristics as we changed from standard jet fuel to a fuel that was a blend of a fuel that was made from camelina plant oil, and also added 50% of Jet A to that. There are some other groups out there. Tyson Foods is making a biodiesel and biojet fuel from chicken fat that they sweep up on their processing plant floors. So there's a number of different ways of making these alternative fuels. All of them result in a fairly clean kerosene that doesn't have nearly the contaminants in it that the fuels from refineries do. The fundamental thing is the aircraft has to retain its performance characteristics when you burn a fuel. You can't have any drop in power. The fuel also has to have similar characteristics in terms of density and volume to kerosene. So what we're looking at is drop-in fuels. A lot of the fuel systems on the aircraft are designed to rely on the aromatics in the fossil fuels to swell the seals to make them leak tight. So when we fly an alternative fuel, we have to mix it with standard fuel to retain those properties. Otherwise, the fuel would just leak out of the aircraft. And then the second thing we're looking at is just the emission characteristics. By that I mean the amount of pollutant generated per kilogram of fuel burn.
After the first few flights, it was shown that using these types of alternative fuels could significantly reduce emissions at cruise altitudes, particularly soot emissions. Work continues to better understand how to use these fuels and how to make them even more efficient for future aircraft. Other than alternative fuels, there are some other ideas out there for finding more efficient ways to power aircraft. If we look on our roads today, many of the cars that are now being driven run on a combination of fuel and electricity. The idea that aircraft could do this seemed far-fetched only a few short years ago, but today, this idea is gaining traction. There are several ideas on how to do this, so let's take a look at a few. Here, a team is looking over a new Boeing aircraft design called SugarVolt. This unique design has several interesting changes, like the truss-braced wings that have the potential to reduce the drag of the wings by making them longer and thinner. Because thin, long wings have the tendency to flex more, designers have included a clever, efficient truss structure to support them. This design has the potential to reduce drag and weight, thereby making the craft more efficient to operate. At first glance, those unique structural changes may look like the biggest game changer for this type of aircraft, but the Sugar concept holds another surprise as well.
In the case of the Sugar concept, what's less obvious to the eye when you see it is that it has an unconventional propulsion system. It's a hybrid gas-electric concept that's closer to what you see in a Prius. It has batteries and a gas turbine engine technology. It requires advances to battery technology, but those are happening throughout the world independent of the aerospace industry, and we're trying to leverage that. We do it on cars, we should be able to do it on airplanes eventually. The challenge is to take those batteries and have enough energy or power content and have them be lightweight. Where we are today, I think, is we're at the dawn of the age where we can start to see electric propulsion or hybrid electric propulsion. And you'll see it on smaller aircraft first before you see it on the large commercial transports. But that's what we're working towards. That's good for cleanliness, it's good for noise, it's good for energy efficiency. It has its challenges. That's why we're working on it, and that's why it's not being done today.
The idea behind this vehicle is to have its twin engines burn fuel when great power is needed, like at takeoff. But when the craft is in a cruise configuration, a switch can be made over to a battery electric mode to supplement or even replace power to the engines. If successful, this could reduce the amount of fuel burn by up to 70%. Another concept called turbo-electric propulsion is being studied here at the NASA Glenn Research Center. Here is NASA's Jerry Brown to explain.
There's not been electric airplanes except in very small size. And the reason is that electric motors and generators tend to be too heavy for flight. We're hoping to change that, and we're hoping to get a benefit from saving a whole lot of fuel in the process. The type of electric propulsion that we're talking about today is turbo-electric propulsion. We're going to keep the turbine engine because it's really good as far as a lot of power in a small power plant. And then we're going to use its power to drive a generator, send electricity to motors that drive fans that do the propulsion.
This concept will look very different from vehicles of today as well. Potential designs include 2 large turbine engines on the wingtips that will drive 2 large generators inside the body. The generators will in turn power a number of fans, providing the propulsion the aircraft needs to fly.
What we want to do here is we want to be able to break the turbine engine from the fan, and that gives the aircraft designer a lot of freedom. If he can move the turbine engine somewhere else in the airplane, that may itself have advantages. The engine and the fans don't have to turn at the same speed. You don't even have to have the same number of fans. And that's what we're really looking for, is we want to have an array of a whole bunch of fans, maybe 15 of them, say, and just 2 engines. You like to keep just 2 big engines because the big engine is much more efficient.
This idea is intriguing, but big changes need to be made to make it viable. One major challenge is the need to reduce the size of the generators, because the generators of today are way too big to fit on an aircraft. One idea that the NASA team is looking at is a way to remove the current type of copper windings in the generator and replace it with superconducting material. This change would allow the generators to shrink, making them viable to fit on future aircraft. As we've seen so far, new aircraft designs are coming online that have the potential to greatly improve aircraft efficiency. Another of these revolutionary designs has come out of a joint MIT and NASA study. This unique design is called the double bubble and has the potential to reduce fuel burn by up to 70% as well.
So the MIT-8 double bubble design was something we've been working with MIT for a number of years on that. The idea there is to take some of the lift that you would normally get from the wings and try and move that to the fuselage. Another thing that's done to enable laminar flow on this vehicle is to reduce the sweep of the wings. It is easier to maintain laminar flow if the wings, instead of being swept back like a lot of modern commercial transports, are more sort of perpendicular to the side of the body of the plane. Another aspect of the D8 that we didn't really discuss is something you can see in these pictures behind you. You can see the picture on the right, which comes from CFD. The engines are what we call in the potted configuration. They're potted separately off to the side. The idea is we hope to get an airstream that's relatively untainted by what's happening over the airplane, a fresh airstream to go into that engine and create our propulsion. The image in the middle, on the other hand, the engines have been moved to inside that pie tail configuration. And by doing that, we actually get some benefits. If you can use the engines to refill that area of dead air behind the plane, you have a chance at being more efficient in terms of propulsion for that vehicle given a certain amount of fuel. We're trying to sort of push the envelope, see what is the maximum benefit that could be obtained by this kind of a configuration to understand what's really possible in terms of fuel savings.
Aiding much of the work is improved computational fluid dynamics and wind tunnel testing.
Right here in this building, we have Pleiades supercomputer, which is one of the largest supercomputers in the US and in the world. It has 200,000 processors working on the problem if you use the whole machine on one problem. So it's a very large machine, and we need that very large machine because we need to do very big problems here at NASA. The Aeronautics Research Directorate that we're using it for is to try and simulate the flow over these N+3 configurations. So in order to capture all the detail you'd see on a vehicle like this, including what's going on inside the combustors of the engines and things like that, you need to have a lot of grid points to resolve all the fluid motion inside those engines, over the airplane, and having that many grid points to resolve all that physics in 3 dimensions creates very large computational grids that require very big machines to advance the equations that govern the fluid motion and get these CFD, computational fluid dynamics solutions that we use to make our assessments.
Aerodynamicists of today are able to model ideas on computers, which allows them to test many different configurations before a wind tunnel model is ever built. Once a design is agreed upon, a wind tunnel model can then be fabricated and tested. This process was used for the double bubble as well, but the wind tunnel test showed surprising results.
The good news is that we've just completed the first test of this configuration in the Langley 14 by 22 wind tunnel at NASA Langley, and it showed even a greater reduction or a more fuel efficiency benefit to this technology than we had predicted on paper with our low-OR models. So we're trying to digest the experimental data that show this nice benefit in fuel efficiency from this configuration. At the same time, we're also using the supercomputer here at NASA Ames, the Pleiades supercomputer, to do computational fluid dynamics CFD runs of these same configurations and see if we can confirm that benefit on the computational side as well.
Testing will continue on the double bubble, and if the results hold, you may see this type of aircraft at an airport near you in the future. When testing aircraft, many different stages occurred. We have already mentioned CFD and wind tunnel testing, but another tool in testing future designs is to build a flying scale model. Although CFD and wind tunnel modeling is the mainstay, often test flights of these small, scaled-down versions of an aircraft offer some of the most dramatic results for researchers. That is the case with this aircraft, called the X-56. This aircraft is being used as a test bed to understand how different wing configurations work and how a unique idea called active control may be used in the future.
The whole concept behind the X-56 is that they've long known that a very long wingspan vehicle is more efficient than short wingspan vehicles. Problem is, though, when you get a very long wingspan, you start to get into issues with flutter modes that start to creep into the vehicle, so the wing will go unstable and in extreme cases will rip off the vehicle. To get around that problem, you can use active flight controls to suppress those flutter modes. Active control is you put things like accelerometers within the wing, and as soon as you sense that the wing is starting to get into these flutter modes, you use the control surfaces behind the wing to damp that out. So the airplane, as it's flying, is continually fighting these modes and keeping the wing straight and stiff. Then you can build a lighter, longer wingspan vehicle that is more efficient. This vehicle, as funded by the Air Force, was built as a multi-utility technology test bed. They call it the MUT for short, and it is built to do a lot of different kind of testing in aeronautics. The wings are removable. You can put on a stiff wing, you can put on a flex wing, you could do a joined wing configuration. We can learn quite a bit from testing this kind of vehicle. Right now, the focus is on flexible wing and active control of flexible wings, but in the future, there are many experiments that can be done with this vehicle.
The research on the control of lightweight, flexible wings being performed today on the X-56 is key to enabling the long, thin, low-drag, and low-weight wings of tomorrow's N+3 configurations. Much is going into understanding what it will take to improve the already incredibly efficient aircraft of today into ultra-efficient vehicles of the future. Although we don't have all the answers yet, it's clear that NASA and its brilliant engineers and researchers are helping to lead the way to a safer and more efficient way to travel.
We are nowhere near the maximum that we can get out of this industry. And there is a lot of work to do, and that's what my team is doing. That's what we're doing within NASA, and I cannot wait for the future.
This is Mission Control. National Symphony Orchestra, you have permission to launch. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and liftoff.
NASA has blazed a trail, and it has transformed all of our lives by blazing that trail. The way we communicate, the way we navigate, the way we produce food, the way we produce energy, the way we predict weather and understand the Earth. All of these capabilities that, in many cases, these capabilities we take for granted as Americans, are available to us because of the trail that NASA blazed.
A lot of the technology that we have today that a lot of us take for granted wouldn't have been possible if it wasn't for a lot of NASA's work. A lot of the systems that we use today in our cell phones, if it wasn't for a lot of that R&D that NASA was doing back then, we wouldn't have what we have today. So whether you're exploring space or just trying to solve problems, technical problems, NASA has done a lot of that heavy lifting for a lot of us.
I was going to be a part of this celebration for NASA's 60th anniversary no matter what, because, I mean, I grew up loving NASA.
NASA called me, and whenever NASA calls me, I say yes.
To me, it seems kind of obvious. I think space exploration and science is something that deeply inspires everybody.
In a world filled with bad things, NASA was doing things for good, and I always loved that about it.
I'm just a huge fan of NASA in general. I think it's the missions that have happened and continue to happen are a kind of poetry that is the most moving thing we have right now, this sort of age of exploration.
The ideals of NASA, peace, exploration, science, courage, these are ideals that we want to celebrate.
In the next 6 years, I see NASA experiencing an explosion of creativity from the young people.
I would love to see them go to Mars. I would love to see a person walk on Mars. I think that would be amazing, because when you talk to anyone in the world who was around when they landed on the moon, the thing you hear that is the common thread is the world stopped. Everyone just came to a complete standstill for one moment to realize that we're all just this one blue planet.
I want us all together to also look to the future, because we have a plan to send humans back to the moon and then onto Mars. We have the most amazing rocket designers on the planet building the systems right now that are going to take humans farther into the solar system than ever before.
Scott and I heard it was your birthday, so we thought we'd sing you a little song. Ready? 3, 2, 1. Happy birthday to you.
Hi, I'm wishing NASA a very happy 60th anniversary.
Happy 60th anniversary.
Happy 60th anniversary to NASA.
I want to wish you a happy birthday.
Happy 60th anniversary, and thank you for all of the endless inspiration you've given me over the years.
Happy birthday, NASA.
Tonight it's my pleasure to share with you the official logo that will be used to observe these milestone anniversaries.
things that you probably didn't know about me. Probably number one, our family has 2 dogs who really think they are brothers. And one is a 130-pound French Mastiff named Boss Hog. And the other is a 12-pound miniature dachshund named Oscar. And they run around together and they think they are absolute brothers and absolutely the same, but they are absolutely the heart and soul of our family. Number 2, our family absolutely loves to watch Aggie baseball. It's one of the favorite things that we do together as much as we can, certainly during baseball season in the spring. And in fact, it was the last thing we did before coming out to Russia to prepare for launch. We watched the Aggies play baseball at the University of Tennessee. Number 3, I actually do still practice medicine. I'm an active physician, and one of my favorite places to see patients is at a free clinic in Galveston, Texas, where we practice medicine for the underserved and those who can't afford medical care and do not have insurance, and that's at St. Vincent's House in Galveston, Texas. Completely student-run free clinic, but it's one of the joys. I love going there, and I love seeing my patients, and it allows me to teach medical students and residents really how to practice medicine in an underserved environment, and something I enjoy doing every week when I'm able. Number 4, my husband and I had a very non-traditional wedding on a 1,000-acre ranch, and part of our wedding reception, we actually had a rodeo event, and there was a big calf roping event that occurred, and most of our guests say they had never ever been to a wedding or a reception like that, but thought it was the best thing they'd ever been to. Final one, number 5, something many people do not know about me is that when I was getting my bachelor's degree at the George Washington University, I also needed to work to earn some money. And so I actually taught martial arts. I taught Kung Fu to school-age kids from age 5 to about 15. And I would do that 3 times a week, and that's how I earned money in college, teaching martial arts.
Liftoff of the Atlas V.
"2020 will be a banner year for the exploration of Mars. In addition to the launch of NASA's Mars 2020 rover, the European Space Agency and Roscosmos are sending the ExoMars rover to the Red Planet. As it descends from its landing platform, ExoMars will embark on an enterprising mission to uncover buried signs of past or present life. The Martian surface is a harsh environment, bombarded with cosmic radiation, but the subsurface could offer better protection. For this reason, ExoMars is equipped with an extending drill that can retrieve samples from up to 2 meters below the surface. Studying these samples will be the job of the Analytical Lab, a trio of instruments designed to search for the molecular fingerprints of life. The Mars Organic Molecule Analyzer, or MOMA, is the largest and most complex instrument on the rover. Its mass spectrometer subsystem and its main electronics were built and tested at NASA's Goddard Space Flight Center, which also contributed mass spectrometers to NASA's Curiosity rover and MAVEN orbiter. MOMA is designed with a mix of proven hardware and innovative new technologies. Here's how it works. In gas chromatograph mode, crushed Martian rock is put into an oven and heated to 900 degrees Celsius in just 2 minutes, vaporizing the sample. Molecules of hot gas rise up and flow into a narrow 20-meter-long tube. Special coatings inside the tube cause molecules with certain chemistries to slow down more than others, separating the mixture of molecules over time. Next, a beam of electrons ionizes the molecules, giving them a positive electric charge and deflecting them towards the linear ion trap. The ions are caught by a fluctuating electric field and sent to a detector to determine the chemical makeup. While gas chromatography has been used to study Mars since the Viking program, MOMA has a second method for preparing samples that has never been used on another planet. In laser desorption mode, a sample is placed beneath a powerful ultraviolet laser. A beam of energetic light builds within the laser and fires in a billionth of a second, concentrating its energy onto a spot smaller than a grain of sand. This rapidly vaporizes a portion of the sample, releasing large organic molecules that could be broken down by oven heating. The laser shot also ionizes some of the molecules, allowing the vapor to head directly to the linear ion trap. Neutral molecules are ejected by a vacuum, while the remaining ions are sent to the detector to determine their chemical makeup. Laser desorption will enable MOMA to detect long molecules, like lipids, the building blocks of cell membranes, a leap forward in the search for life on Mars. MOMA's linear ion trap is another first for the Red Planet. It will scan for the fingerprints of life using techniques normally confined to laboratories on Earth. One technique, called SWIFT, repeatedly ejects unwanted molecules from the trap. Over time, this builds up molecules of interest, improving detection. Another technique is tandem mass spectrometry, or MSMS, which identifies large molecules by breaking them apart and analyzing their fragments. By combining SWIFT and MSMS, MOMA can determine an individual molecule's formula and its structure, both important criteria in the search for life. The question of life on Mars is among the most important in planetary science, and the evidence may be buried just below the surface. With the help of MOMA, ExoMars will take us one step closer to uncovering the answer.
In 2014, NASA sent its Global Hawk aircraft out over the ocean to study Hurricane Edouard. This remotely piloted vehicle collects data like temperature, relative humidity, and wind speed to better understand how hurricanes intensify. Sometimes clouds block the measurements taken directly below the aircraft, so the scientists drop individual instruments that parachute down to the surface. These dropsondes also measure the wind speed and direction as they fall. Near the surface, especially in the center of the storm, the deep red to orange color indicates there is plenty of moisture for the storm to draw on to intensify. The result is a well-defined circulation of winds, which are strongest near the storm's center. During Hurricane Edouard, dry air near the center slowed intensification. But then, just before a period of rapid intensification, clouds and precipitation moved into the dry region, bringing moisture. Did the movement of moisture cause the rapid intensification? Or did the stronger winds at the onset of intensification cause the clouds and precipitation to move? Studies like this one will help us learn that answer.
Throughout the universe, there are forces fundamental to how things move. Just as gravity is key to how things move on Earth, a process called magnetic reconnection is key to how charged particles speed through space. The more we understand how those particles are accelerated, the better we can protect our spacecraft and astronauts as we explore deeper into the solar system. And now, NASA's Magnetospheric Multiscale Spacecraft, or MMS, has discovered magnetic reconnection occurring in a new and surprising way near Earth. Typically, images of our planet from space show a blue-green sphere engulfed by the darkness of space. But invisible to the eye, a vast network of magnetic energy and particles surround our planet. Earth's magnetic field creates a protective bubble that shields us from highly energetic particles that stream in both from the sun and interstellar space. As the solar wind bathes our planet, Earth's magnetic field lines absorbs this energy and get stretched. And like elastic bands, they eventually release energy by snapping. As a result, particles in the region are flying at supersonic speeds. That burst of energy is magnetic reconnection. It's pervasive in the universe. It happens on the sun, around Earth, and flings particles across the solar system. Scientists have observed this phenomenon many times in the magnetosphere, Earth's vast magnetic environment. Now, in a new study, MMS caught the process occurring in a new region. For the first time, magnetic reconnection was detected in the turbulent magnetosheath, the boundary between the magnetosphere and solar wind. This region is made up of turbulent plasma. It's one of the most chaotic regions in the near-Earth space. MMS captured 3D observations by flying 4 identical spacecraft in a tight pyramid formation through the magnetosheath. These arrows show the hundreds of observations MMS took to measure the changes in particles and the magnetic field. This is the moment MMS sees bursts of energy from magnetic reconnection. But these signatures don't look like standard reconnection. Compared to standard reconnection that occurs over tens of thousands of miles, this new magnetic reconnection spans only a couple of miles within turbulent plasma. These reactions are essentially much smaller but more stretchy elastic bands that accelerate particles 40 times faster. In short, MMS spotted a completely new magnetic mechanism that's much quicker than we've seen before. Just like when you mix milk into coffee, turbulent plasma in space moves randomly and creates vortices. It can transport particles and energy, but a lot is unknown about how these particles move through these regions. Showing that this new magnetic reconnection plays a role in turbulent plasma gives scientists insights into how turbulence influences particles moving through space. By looking at such fundamental processes in space at both large and small scales, scientists can learn what drives the complex environments we travel through to explore our solar system and beyond.
Hi, I'm Amanda DeBelly-Schauer. I'm an undergraduate student right now at Old Dominion University, and I helped work with Bob, the tick-killing robot, last summer here at NASA Langley, and we actually protected the CDC, the Child Development Center, from ticks.
My name is Lexi White. I'm a PhD student with the ODU Tick Research Lab. A TickBot is a tick-killing robot. It's semi-autonomous and follows a predetermined outline perimeter that you lay out. And it can actually protect an area, providing immediate relief from tick encounters for 24 hours.
If you would, for the NASA audience, just share with us what your background is, education, where you went to school, what you studied, ultimately what you did as a career, and then how you came to become an astronaut.
I went to St. John's University in Minnesota, where I got a bachelor's degree in physics. I was in the ROTC program, so immediately after graduation I became an active duty Army officer, served as a combat engineer, and then at a certain point in my career I got the opportunity to go to graduate school. So I got a master's in applied physics from Stanford University, used that to teach physics at in the physics department. Actually, it's the Department of wow, they're going to be mad at me if I miss it. Department of Physics and Nuclear Engineering.
Good.
At West Point. And after that was done, in that process, I had studied space physics, so I got very interested in that and transitioned to becoming a space operations officer for the Army, which led to me being invited to work at NASA as kind of an experiment in having an active duty Army officer with a space operations background working in the astronaut office.
Awesome.
And I got to know a lot of astronauts, so I really enjoyed working with them, and because of that, was really inspired to apply.
Yeah.
Because of the combination of physical challenges and mental challenges. And I was fortunate enough to get hired in 2009 to be an
So
astronaut.
for a lot of people that are watching, maybe they're not familiar with what a combat engineer is. Can you share with us what that is?
Sure. A combat engineer helps out with ground tactical units with making sure they have mobility. So for example, if you run into an obstacle, then we try to help break through those obstacles. There's also survivability we support where, for example, if we're setting up a big defensive area, we can help harden the position to try to protect soldiers from...
So you're making real-time decisions that are life and death in critical moments. Is that safe to say?
That's safe to say for any military officer.
Sure, absolutely. Awesome. Joe, give us a little bit about your background, education, where you went to school, and ultimately your career, and then on to the astronaut corps.
Sure. So I'm a Southern California kid and went to school, University of California, Santa Barbara, then off to get a master's at the University of Arizona, both in geology. So I'm a rock guy.
Good.
And worked a bunch of different jobs while I was at school. I was in the U.S. Marine Corps Reserves, worked as a hydrogeologist, managed the research center out in the Bahamas. But before I became an astronaut, I was actually a high school and middle school teacher. And so in 2004, NASA wanted to hire some educators to become teachers, and I was one of the lucky 3 that got selected.
Awesome. So you obviously spent a lot of time on the space station talking to young folks, I presume.
Yes.
Was that one of your duties?
It is. It's all, all of our duties while we're up there is just to share what we're doing with school kids. And the one part that's hard as a teacher, you kind of gauge what you do by looking at your students. Are they bored? Are they falling asleep? Are they engaged? But while you're in space and you're doing one of these downlinks, you can't see them. So it's hard because they can see you.
They can see you floating.
They can see you floating, doing all that, but you can't see them, and that's probably the most challenging part.
I'm pretty sure you kept their attention.
I think we did all right.
The feedback we got is that worked.
Absolutely.
Yeah.
Well, great. Well, I have some questions. I sent out a tweet yesterday asking people if they had the opportunity to ask you any questions, what would those questions be? And I have a number of questions here from some of the folks that follow NASA. And I'll just start with one here that I think will be pretty easy for you guys to answer. What do astronauts do in the Soyuz capsule while you're on your way to joining the International Space Station?
We double check everything. The Soyuz spacecraft does a lot of things autonomously, and we have to double check that it's working well. And it's also got a lot of redundant systems, which for spaceflight is very important. So we're ready and trained so that if one of those automatic systems fails, we can take over those things manually.
How much time did you have from the time you launched until you docked?
For the flight that Joe and I were on, it was 6 hours.
Okay. And is that common or uncommon? Sometimes it takes multiple days, right?
Yeah.
Yes.
On my first flight with the Russians, it was a 2-day rendezvous.
Okay.
And so it all depends on the orbital dynamics, where's the space station when you launch. So I think we enjoyed the 6 hours because the Soyuz is small, and you can imagine the 3 of us in that capsule for 2 days. It's a long time, so you're ready to get to the ISS.
I can imagine. Another question is, how long did it take you to get used to 1G once you got back?
I think it varies for everyone. For me, the hardest part is my vestibular system, the balance, where the first 20 hours, if I stood up, I was not feeling too good. Muscle-wise and strength, it was pretty good. But after a day, I got better. But it's amazing what the body does and how quickly it recovers. Where it's just, almost every minute you're getting better and better.
So were you able to walk?
I could walk with a little bit of assistance.
Okay.
Yeah.
Awesome.
It's just you know, you turn your head and you feel like, you know, the floor is moving. If you can imagine being on a boat all day.
Sure.
And when you get off the boat and you kind of stand there, you can still feel
Yeah.
kind of the waves underneath you. It's kind of like that, but just a little more extreme.
Got it. How about you, Mark?
I felt pretty good. Like Joe mentioned, I'd certainly had the feeling that things weren't working quite as the way they normally would. And the biggest issue for me was a lot of soreness in the smaller muscles that help us balance. And I could feel that. Even just sitting up in bed was hard.
So what was your first meal when you got back? And how long did it take before you were ready to eat?
I was ready to eat right away.
Okay.
He's always ready to eat.
Yeah, I'm always ready to eat. My mom might be mad at me if I said this is my first meal because it was chips and guacamole that I had on the plane.
Well, you deserved it.
Thanks.
It tasted good.
It was amazing.
Yeah. Chips and guacamole. What was your first meal?
So we had some, you know, small snacks on the plane, but the meal I asked for when I got back, because I was not going home to Mom's cooking right away, was to have some local oxtail. It was tasty.
Is that right? Oxtail. That's an interesting choice.
Yeah.
Fantastic. Okay, so another question. What is the least known fact about the ISS? And Mark, I'll let you go first.
I'd say it's the amount of science experiments we're doing. For Joe and I, we were up on the space station for 168 days, and in that time period, there was 284 roughly experiments that happened while we were there. So there's an incredible amount of science that's going on. A lot of it without us even having to interact with it.
Awesome.
Yeah, you know, I think people don't realize that we have had, you know, humans, astronauts on the space station for the last 18 years, 24/7, 365. Living in this self-contained environment. So you can imagine, you know, the recycling we do here on Earth, the natural and the man-made. We recycle pretty much everything we can up there.
Awesome. As far as space debris, I've got a question here. Folks are interested in, can you see it from space, and what do you do about it?
Well, hopefully we won't see it. If it's big enough that we can see it, we'll try to go ahead and change the orbit of the space station. So people are tracking that for us, and we can actually do that. And it probably happens a few times a year that we'll change the orbit for objects that are large. The smaller objects, we see evidence of that. If you go out and do a spacewalk, you might see a ding on a handrail. We have the cupola, which is the big window that we look out of, and you can see where that has been struck before. Luckily, it's a
strong window.
It's a strong window, a little bit bigger, but it almost looks like it would look on your car when you get a little piece of rock that hits your window.
Awesome. Did you see any space debris?
I saw the same evidence during spacewalks that Joe mentioned, certainly looking out the cupola like he mentioned. One other thing, Paolo Nespoli, an Italian astronaut that was on board with us during the first half of our flight, he took a lot of pictures and captured some natural space debris interacting with the atmosphere. He actually saw the debris only when it started burning up, and then you could see the flash of light as it finally was completely burned up.
And is that video still out there somewhere?
I don't know if you got it out. I'd be surprised if it wasn't.
It is out there, and it's pretty cool to see.
All right, here's another question from one of our fans. What is your favorite geological feature to look at and admire from the space station?
Well, yeah, so yeah, as a geologist, you know, it's just, you're in heaven, because now you can see everything from a grand scale. So if we're talking geological, I really enjoyed flying over Africa. Not only can you see the different colors of the different rock formations, you can see the dunes, seeing mountain ranges. I mean, there's just, the Earth is pretty beautiful, and you know, it's hard to pick out one, because every time you look out the window, you see something new.
And for me, I think it wasn't so much a geological feature. Certainly deserts. Deserts are particularly impressive because there's less moisture in the air, so you get a better view through the atmosphere of the desert. The time that was particularly impressive for me was looking at the American West I got a view all the way from Denver. When I looked later at the picture and tried to map out what I was seeing, I could tell that I was seeing the lights from Denver all the way to the lights of Houston in one view.
Oh, wow.
Which is really amazing, particularly when the view is at night under a full moon, because the full moon would light up some of those colors of the desert, but you still got the city lights to show where those people were and help you figure out what you're looking at.
So here's a question that is of interest, but maybe not serious. What's it like to sneeze in 0G? And how do you do it?
Away from everybody else.
Away from everybody else, there you go. Is there, I would imagine sanitation on the ISS is critically important. Can you share some of your experiences with getting ready to go fly and then ultimately being on the ISS and some of those things?
We do go into quarantine a couple of weeks before we launch to make sure we don't take anything up with us. And one of the great things about being up there is that, you know, once you get there, you're in a pretty good and sterile environment in terms of, you know, cold and the flu. And so we missed the flu season while we were up there, but it takes a lot of work, not only protecting us before we get there, but we spend a lot of time cleaning up the space station as well.
There's weekly house cleaning on the space station, just like you would do at home.
I can imagine.
Every Saturday morning, got to clean the space station.
Vacuuming and wiping down things.
Absolutely. Yeah, as a Navy guy myself, being on a ship, critically important to keep everything as clean as possible, because if one person gets sick, everybody gets sick, and it happens fast. I would imagine on the ISS, that's every bit as true, whether there's 3 crew or 6.
Mm-hmm.
So that's great. Another question is, and a number of these, just launch. When you launch on a Soyuz, what's it like? What's the jolt like? Is it smooth? Is it harsh? What's it feel like when you launch on a Soyuz? Or do you even remember much of it?
Go for
I
it.
definitely remember the launch. We trained so much in a simulator that did a really good job of getting us used to that small space, that because it was so smooth, I was a little disappointed that it wasn't going to give me a better story out of it. Yeah. Because I had a little window over here, and certainly the view out that window was different from the simulator, but it was kind of hard to get it, and most of the time it was just the blackness of space. So, and the one thing that was very different was when we went from one stage of the rocket to the next stage, there would be a momentary stopping of that acceleration, which felt like a jolt forward. Sure. So that was shocking as we changed it, but otherwise it was very, very smooth.
Yeah, until we got to the space station, and it's a funny story, Mark can
you're talking about my, as we were approaching?
So you go through the whole launch sequence. You have a few hours, like Mark said, you're just checking out the systems, and then you start to approach the space station, and you get your first glimpse out the window of this beautiful, laboratory that we built. And then Mark,
which just happens to be at the same time as the commander, who's looking at the space station through his periscope. It's a very intense time for him because we're approaching another spacecraft, and he's got to be very ready to respond to a failure of the automatic system because he has to do it manually, possibly. So it's very intense for him, and I'm trying to support him all the time. But I get this view of these massive solar rays out the window, and I was like, wow! He just looked at me and gave me a quiet sign.
We were hot mic'd, so everybody could hear everything we're saying, and I'm sure
I was very excited.
Yeah.
So how much do you sweat during all that?
The suit, we're connected to a ventilation system.
Oh, okay.
So if we're sweating a lot, it gets dried up, as long as the suit system's working well. We've had a lot of simulators where we sweated a ton. Yeah.
I think it's a lot easier, I think, real time. Just
the simulation.
You've trained for so long and you're ready for it, and you're pretty prepared.
So final question for both of you. Both of you have been educators in your day. And I got a question here from a 4th grader. Did you use algebra when you were up there?
How can you not use algebra? Every day, no matter what you're doing, there's algebra that is involved.
Awesome.
Yeah, it's pretty important.
One of the most important things I think that NASA does in its mission is inspire young people to learn science, technology, engineering, and math. And of course, it's not just the astronauts who are our heroes that need to use these skills. It's also all the people that design and build and integrate these amazing capabilities for our country and for the world. So I just want to thank you both for being here. Thank you for your service to this country. Thank you for your service to NASA. It's one of the best parts of my job is getting to sit down and talk with folks like you. You're both great Americans. So Mark Vande Hei and Joe Acaba, thank you for your service, and it's good to be with you.
Thank you, sir.
You bet.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.